Hi, I'm Mark, this is Alice, and our project is ColourU. So since the beginning of photography, people have wanted to add color to grayscale images, and in modern times, this takes a painstaking amount of time and effort in Photoshop. So naturally, neural nets came out to automatically recolorize images, but they have some problems. They don't allow the user any control, and the quality of the recolorization is somewhat poor, as there can be some gray patches and things it doesn't know how to colorize. So ColourU gives the user more control over the recolorization process, allowing them to add color hints to the neural network. So we have ColourU in a GUI, simple GUI, to load the images, and you can place the color samples, and then you can click the recolorize button and you get this, the recolorization. Our data comes from Tiny ImageNet. It's a data set of images from Stanford University. There are 200 different classes, but we only used 5 to narrow down our scope. There are 500 images in each class, and they are 64 by 64 pixels dimensions. So in order to process the data, we did this all automatically. We converted it into grayscale by converting it into the LAB color space. And by zeroing the A and B layers, we get the grayscale representation of the photo. We randomly selected squares to have their full color preserved, as you can see here. And then we applied a high-pass filter on the grayscale version and appended that as a 4th color channel for better edge detection. You can see that here. There are a few limitations though. Samples placed on the edges could have both objects, like the edge between objects can have both objects be colored the same way. So this here might have the water surrounding it be colored orange. Samples could not be placed on some objects. If you look here, there's no sample on the ground, and the neural net might not know what to color it. And the high-pass filter might miss some edges just because they don't really appear in the grayscale image, and so it can cause the color to sort of bleed out.
So the overall structure of our neural net is a GAN model with a generator and a discriminator. So for our generator, we chose to use a U-Net-inspired model, which consists of 5 down convolutional layers, 5 up transposed convolutional layers, and the output feature images from the convolutional layers are then put through another convolutional layer and then appended to the corresponding feature image in the transposed convolutional layer. The output of this generator is a two-channel 64 by 64 pixel image, which is then appended, which forms the AB layers of the LAB image, which is then reappended onto the L image to form the full 3-channel LAB image. So for our discriminator, we chose to use a very standard convolutional neural net model with 3 convolutional layers and 2 fully connected layers, along with batch normalization, leaky ReLU, which is also used on the generator, and max pooling.
So in order to discuss results, our quantitative measurements do not include accuracy. This is because there is not really a concept of accuracy when it comes to generators and autoencoders. So we instead tried to substitute with normalized loss. And that's, in this equation, you take the loss between the generated image and the original image, as you would, and then you divide by the loss between the grayscale image and the original image. And so we're ideally looking for loss closer to 0, but definitely loss less than 1. Our qualitative measurements include just, you can kind of look at the image and get a sense of sort of flaws, if there are gray patches, if it doesn't preserve the colors of the inputs, if it doesn't really detect the edges very well. We want to compare it to the similarity to the original image, and also we want to ask ourselves, is this convincing on its own without having an original image?
So for the results, since we trained our model on 5 different categories, it is possible that the model would perform differently for images from each of those categories. So as a result, we ran the model and produced results on test samples from each of the 5 categories we trained on. So we're kind of going to go through them all. So the first one is fish, with the normalized losses displayed on the bottom with the images, the real original images on the top, the input to the neural net in the middle, and the generated image on the bottom. As you can see, there are different quality in generated images, depending kind of on the color samples and the original image. One thing that our model kind of performs more poorly in is very saturated images, which is kind of understandable as highly saturated, like very bright image colors in the LAB format have very high pixel values, and it could just be that our neural net is not being able to output those values. So salamanders, as you can see, again, there's varying qualities of results. Frogs, toads, which are very separate categories, and alligators. As you can see, one of the things that is kind of coming up in the generated images of the neural net is that it's introducing other colors that were not suggested by the inputs. Some of this is due to the images that it was trained on. Given that the categories it was trained on, like orange is a very prominent color that occurred a lot in the in the training set, and that it's very common for the goldfish to be very bright orange colors. And as you can see, it kind of introduces those colors in images where it doesn't really have a color hint. And so in addition to that, we also sourced images from varying other places on the internet, including images from categories that the neural net wasn't trained on, such as, in this example, butterflies, rhinoceros, rabbits, and tigers. So as expected, it performs kind of poorly there, and we also did it for larger images. So one of the things, yeah.
Almost done.
Yeah, sorry. One thing I kind of wanted to mention was the third image of the goldfish. In the smaller image, it kind of went outside of the lines, but in the larger image here, it's very clear that the edge detection is helping the model. However, in this case, it's also very clear that our model mistook the inside of the fish with the outside of the fish and inverted the colors. And so here are some suggested improvements in future iterations.
That's it.
Do make sure that you practice for timing. It's quite important, as you can see. It's great, actually. It's a tricky problem, and it's hard to do. It's nice to see how far you got. One thing, just to be clear, I'm not sure, I know I read it in your reports. The input includes hints from the user, is that correct?
Yes.
And it's a human that's doing that?
Yeah.
Not
In the actual use in inference mode, yes. For data processing, because we couldn't do it all ourselves, we had it automatically done.
Yeah.
So you pick some from the correct answer and annotate it. And is that where the edge detection showed up? You were making use of edges to select where you wanted to do that, or what was the edge detection about?
Edge detection, it's done in inference mode as well. You take we apply the edge detection filter on the grayscale image that's inputted. But the point is just so that it colors within the edges, hopefully.
Just another additional input to the neural net to help it be able to better detect edges and color around those.
So you're giving it this specific hint with your red and edge detector, saying, think about this while you're doing what you're doing.
Yeah.
Okay, that's interesting. Mike, do you have any questions?
I didn't see a baseline. How well did your baseline do at colorizing?
Our baseline wasn't really able to work on this slightly more varied classes. Our baseline performed very well on the goldfish, but when we tried to generalize it to these larger classes, it wouldn't really be able to add a lot of color, and that at best it just added one general color to a certain area in the image.
Cool. Any quick question, comment?
Yep.
So I'm a little bit confused. Do you have paired data from grayscale to color picture? Is it paired or unpaired?
We took,
paired.
Paired.
Yeah.
So what would the results be if you just do maximum likelihood? Do like a pixel CNN, pixel RNN, instead of using a GAN? Because I think the optimal use of GAN is, what if you don't have paired data? Then you need to do unsupervised domain translation, and you need to do a cycle GAN, so that you don't even need paired data. But if you use paired data, so just out of curiosity, why would you choose basically a binary output for this kind of GAN style training versus just maximum likelihood?
Our original goal was to have the GAN help. Well, one of the issues that we saw with other kind of non-GAN implementations is that the colors were kind of blurry. It didn't necessarily, there were gray patches and stuff like that. Our original intention was in hopes that the GAN would be able to correct for some of that. Whether or not that actually worked in our implementation is debatable.
And also, just about the GAN, GAN also helps you, instead of restricting valid colorizations just to be similar to the input, it allows you to sort of ask yourself, is the colorization sort of realistic looking?
And that
just in general. Maybe it doesn't have the same colorization as what was input, like as the original image it was based off of, but maybe it produces a valid recolorization anyway. So
That was actually something we saw in one of our sample data that we didn't get a chance to talk about, where the model was able to, without color hints, it was able to produce a realistic looking image, but it just didn't match the original image. And that was something that we hoped that the GAN would help our model to be able to do.
Great. Okay, thank you.